All right, so let's now take a look at a video that talks about why. Why do we set up larger games using a standard max problem? All right, so again, we're trying to find the optimal mixed strategies and the optimal value of the game for a larger game that's not strictly determined. All right, and it's bigger than 2 by 2. So in this case, again, we'll start with an example. The first row is 1, 3, 4. The second row is 4, 1, 0. Now, I want you to notice that all of the numbers in this game are non-negative. All right, that's important in setting up this problem. And we know that if we start off with a game that has some negative numbers in it, the very first thing we do is find some number k and we add it to all those numbers so that we will start with a matrix that has no negative numbers in it. So that turns out to be important in order to create that standard maximization problem. All right, so Q now is, we have 3 columns. So Q will be a column matrix, Q1, Q2, and Q3. But again, the row player has 2 possibilities. They could choose row 1 or row 2. And again, since our expected value is PAQ, our expected value for just row 1 would be 1, 3, 4 times the Q1, Q2, Q3. And we've got our expected value E1. Now, if the row player chooses row 2, our expected value would be 4Q1 plus Q2. Now we've got a problem because setting these equal, it's not going to be as simple as we did with the 2 by 2. We can't just solve for Q1, Q2, and Q3. We don't have enough information here. So this leads us to thinking about this in a different way. Now, we still want the column player to minimize that expected value, all right? Because the bigger the E is, the more the column player is paying to the row player. Now, since capital E is the optimal value for both players, that means it's also the optimal value for the row player. That means E1 and E2 are both less than or equal to that final answer, capital E, which is the optimal value of the game, right? So, in other words, the row player is trying to bump that E up, while the column player is trying to bump it down, okay? So that's an important part of this. Now, again, since all of our numbers in our matrix are non-negative, okay, and they're not all 0, this expected value of this game has to be positive, all right? It can't be 0 because if we look back, the only way it could be 0 is if it were strictly determined and 0 was the value of the game, because if it's mixed strategies, it would be an average score of 0 over playing this game many, many times. And the only way to get an average of 0 is when some are positive and some are negative. So this expected value of this game will have to be positive. Now, we want to, from the column player's perspective, we want to minimize that value of E. But from the row player's perspective, we know both of those E1 and E2 must have to be less than or equal to E. So this was where the E1 and the E2 came from. And we know both of those are less than or equal to E. We also know that the sum of the probabilities is 1. And we also know that all of those probabilities are greater than or equal to 0. Now the problem here is we want to minimize something, and we've also defined 2 inequalities in terms of that same thing. And that's not going to work, okay? So in order to get rid of that E, we're going to multiply all 3 of these first three lines, two inequalities, and the equation by 1 over e. And when we do that, we will get these two inequalities right here. And then the third one will become this equation. Now, notice we could rename each one of these. And that's exactly what we're going to do. We're going to rename q1 over e to be x1, q2 over e to be x2, q3 over e to be x3. So we're going to replace those with new variables, x1, x2, and x3. And so now we've got these two inequalities, and that looks more familiar with our setup that we had, that we've been using. And also this one right here, if we replace those, we get x1 plus x2 plus x3. Now, here's where it gets interesting. We wanted to minimize e, but notice if we want to minimize a number, let's say like a function, then that's the same thing as maximizing 1 over that number. We'd actually talked about that before. So minimizing e turns into maximizing 1 over e, which we're going to call z. This will become our objective function right here. Pretty cool. So we turn this into a maximize linear programming problem. We're going to maximize z, which equals x1 plus x2 plus x3, subject to those two inequalities, both of them less than or equal to 1. And we know our variables are all non-negative because the q's were non-negative and e was also non-negative. In fact, we know we won't have any trouble dividing by e because e is not zero either. So this is going to work in our favor. That was why we needed non-negative numbers in our matrix. All right, now we can see all those ones, right, that we've been using. Now we would solve this just like we would solve a regular linear programming problem. This is a standard max. So we could put this into our simplex tableau and do our pivots and find our x1, x2, and x3. And in order to find q1, q2, and q3, we'll go back up to here, right? And remember, if x1 is q1 over e, then q1 is e times x1. q2 is e times x2. q3 is e times x3. And e, remember, was 1 over z. If 1 over e is z, then 1 over z is e. Both of those are the same. And so our q is 1 over z multiplied by the solution to the LP problem, the column vector x1, x2, x3, just like we said in our problem. And the e is 1 over z plus your k. You've got to add, or excuse me, not plus. Let's make that a minus. There we go. That's a little bit better. Minus your k if needed, right? If we added a k in the beginning to make all the elements in the matrix not negative, then we'd have to subtract that back off to get the correct e. Now, lastly, to find p, well, we'll go through this whole process again, right? But instead of looking at it from the perspective of the column player, we'll look at it from the perspective of the row player. And it turns out that everything is sort of flip-flopped. This one becomes a minimize problem with greater than constraints. And this would be the dual of the standard max problem that we have above. And we know from studying what the dual is that we read the solution of the dual from the bottom row under the slack variables when we solve a standard max problem.